Okay, so we just computed the Galois group of this the splitting field of this polynomial over Q. Now what we're going to do is we're going to investigate the Galois correspondence. So remember, the Galois correspondence was a correspondence between subgroups of the Galois group and intermediate extensions. Okay, so let's investigate the Galois correspondence here. As a quick reminder, our Galois group, when we added in root 2 and root 3 to Q, had 4 elements: the identity, something that negates root 2 and leaves root 3 alone, something that negates root 3 and leaves root 2 alone, and then an element that negates both root 2 and root 3. So let's investigate now the Galois correspondence. Let's start with G. G is, remember, it's a set of subgroups of our Galois group. Let me just be really explicit about what the Galois group is here. And this group was Z4. Now there's actually, or sorry, Z2 cross Z2, not Z4. There's 5 subgroups of this guy. This guy's got 5 subgroups. Let's list all of them. There is, I'm going to adopt the notation of the book. There's the whole group, which is Z2 cross Z2. Sometimes people write that as D4 as well. I don't like that. That makes me unhappy. I prefer to think about it as Z2 cross Z2. There is a subgroup that is generated, A equals, by sigma 2. So sigma 2, if you square sigma 2, right, squaring sigma 2 means negate root 2 twice and don't do anything to root 3. If you negate root 2 twice, you're the identity. So sigma 2 squared is the identity, so we'll add in the identity. There's a subgroup B, which is generated by sigma 3. If we do sigma 3 twice, we're back at the identity. There's a diagonal subgroup, which is negate both root 2 and root 3. If we do that twice, we're back at the identity. And there's, of course, the trivial group, which just has the identity in it, the trivial subgroup. So there are these 4 subgroups of the Galois group. I don't particularly like the notation ABC, but I want to keep with the book's notation. All right, so we have the whole group and so on. So what are the subgroups? Well, in this set G, we have G, the group generated by sigma 2. Let me just write it clearly. Sometimes we'll use these Wrangle brackets to mean generated by. Sigma 3 will be, B will be similar. I'm just copying what we have up there. C is both. And then I is just a trivial group. All right. So these are all the subgroups of the Galois group. Now, in this case, the set of intermediate fields is kind of simple. So we have Q. We have, of course, everything. That's an intermediate field. We have Q adjoin root 2. We have Q adjoin root 3. And there's actually another quadratic extension here. There's Q adjoin root 6. And it's not hard to see that that is all of the fixed fields. It's or all of the intermediate fields, although you'd have to sit there and think about it. So remember, the Galois correspondence was a inclusion reversing bijection between these. So let's go and let's work it out. So I'm going to say what the dagger operation is. So recall, dagger was an operation from G to F that takes a subgroup and looks at the corresponding fixed field. Okay, so let's do that for each of our groups. So what's G dagger? So G dagger is the fixed field for the whole Galois group. So let's think about that for a second. G has an element that negates root 2, has an element that negates root 3, and has an element that negates both of them. And so, let's see. The element that negates root 2 only fixes root 3 and the rationals. that sits inside of it. But the element that negates root 3 doesn't fix root 3, right? It moves it. So we have an element that negates root 2 and root 6, so those aren't fixed. And this other element negates root 3. So neither root 2, root 3, or root 6 are fixed. These are all saying that these get moved. So what's the only element of G, or sorry, what's the only subfield of our extension that's fixed by everything? Well, of course, it's just the rationals. It's just this one here. So G dagger is Q. All right, now let's work out A dagger. A dagger is the fixed field by sigma 2. Sigma 2 negates root 2, but it leaves root 3 alone. So A dagger is Q adjoin root 3. B dagger is the guy that is generated by the guy that, B is generated by the one that negates root 3. So what do we leave alone? We leave alone the root 2. So it's Q adjoin root 2. C dagger, what was C? C was the one that negated root 2 and root 3. So it's this last guy. What does the last guy leave alone? It leaves alone the root 6. And then finally there's identity dagger. What happens there? What does the identity move? Nothing. The identity fixes everything. So this is just everything. All right. So this is explicitly the Galois correspondence in one way. Of course, star just sends things back. Okay, so I won't write that down. Now let's see the inclusion reversing part. So if we were to arrange the Hasse diagram for the subgroup lattice for this setup, identity is at the bottom, and then we have these subgroups A, B, and C, which have more than just the trivial element in it. So these lines means one is a subset of the other one. And then we have that. And now let us do the subgroup, or sorry, the subfield diagram, the intermediate extension diagram. G dagger corresponded to Q. So we have G dagger down here, which is Q. Let me do it in orange just to indicate that's our Q. That's at the bottom now. This G that was on top switched all the way down to the bottom. And similarly, identity dagger is everything. So if I put identity dagger, that's just, of course, everything. That's now all the way at the top, and it was at the bottom. And then we have these A dagger, B dagger, C dagger that sit in between. A dagger was Q adjoin root 2. B dagger was Q adjoin root 3. And then C dagger was Q adjoin root 6. And then now the subset containment goes in the opposite way. Right? So this is what the inclusion reversing aspect of the Galois correspondence is doing. B used to be contained in G, but now G dagger is contained in B dagger. Sorry, I meant to do that in the laser pointer. So we see that happening in this example.